Hey everybody, welcome back to Young Engineers of Today. I hope you are ready to move on to a new subject because that is exactly what we're doing. As you can pretty clearly see, this subject's going to be cybersecurity. Yeah, it's going to be all about the internet and computers and stuff like that. Yeah, figured you'd probably be pretty excited about that. So let's go ahead and get started. But before we get into cybersecurity, since we did just spend time discussing model rockets, I did want to go over this. SpaceX actually just launched um, a used Falcon 9 rocket an hour ago. Actually, let me just double check that, make sure it wasn't scrubbed. Just checking. Okay, so it's going to happen tomorrow, actually. Oh, well, there you go. Highly topical then. But yeah, so tomorrow SpaceX is launching. Um, yeah, uh, a used reusable rocket, which is a big deal because it costs anywhere from tens to hundreds of millions of dollars to replace a rocket, which is actually primarily why spaceflight is so expensive. Imagine you open a restaurant and every time you serve your guests, you toss out all of the tables and chairs and dishware on the inside and then buy new ones. And that's kind of what we've been doing with most of our rockets. Now, the space shuttle was reusable, um, obviously. The solid rocket boosters on the sides of the space shuttle were partially reusable. Uh, the fuel tank, the big orange fuel tank, was not reusable. Um, and the space shuttle was just generally really expensive anyway to launch because it was big and heavy and needed a lot of fuel, and there were a lot of moving parts, so that needed to go through a lot of vetting in order to make sure it was safe. But anyway, um, yeah, this will be the first used rocket launch, so that should be pretty significant. So keep an eye out for that tomorrow. Now, insofar as cybersecurity is concerned, well, there's a bunch of things on this presentation, and we're not going to cover it all today, but we're going to get through networks probably, and we might get started on cybersecurity key terms and current events, but that's about as far as we're going to get today. But networks, cybersecurity key terms and current events, Internet of Things, encryption, and hacking. So it's a bunch of stuff. So first bit is networks. And we're going to start out with a history of the internet, which is a video. Actually, we're going to have a couple of videos to start off. So I'm going to copy the video URL and I'm going to place it into the chat box, and I'll just have you guys watch alongside me. Is that coming out through your guys' speakers? Oh, never mind. Okay, so there were probably a lot of concepts and terms on there that might have just been sort of, white noise at this point. It may have made perfect sense. Who knows? But regardless, this introduces a lot of concepts that we're going to be covering. Well, not really. It's a lead into TCP/IP, which is something that we're going to be talking about as well when we discuss networks and things like that. But that right there is a very comprehensive yet condensed version of a history of the internet. I was trying to find the most descriptive way to put it, but yeah, definitely. Next, we've got the basic concepts of networks. Another one. Let me go ahead and link this one as well. And once you're done watching the second video, just go ahead and raise your hand. Okay, we'll give everybody a few more minutes because not every hand is up. Okay, so that was an incredibly brief and from the very top overview of not just computer networks, but networks in general. I mean, network is a general term, sort of applied to interconnected webs of related things. So you can have a network of friends. You can have like a network of contacts. You can have just a number of different networks. A computer network in this case is the same basic concept, except it's just computers that are talking to one another. But it's obviously this is part of a series of videos that will go more in depth into the specifics that go behind a network. So if you're interested in that, you can go there and spend a little bit more time, going over the different videos that they have and things like that. Now, part of the thing is networks at this point are so large, are so complex, are made up of so many organic parts and things like that, that it's almost kind of impossible to know everything about the internet, how everything works on the internet, how everything communicates and everything like that. I mean, you can understand IP, you can understand TCP, you can understand SSH and things like that, but insofar as how, chances are you'd still come across them and you go like, I don't know what made that work. Like, I don't know why this is working when something else that's set up the same way does not, that sort of thing. And that's just sort of the nature of something like the internet, which is made by hundreds of thousands of different people, not millions, all the time. And that's okay. You don't have to know everything about it. It's just a big, complicated thing. Not to say like, oh, this is about as far as an understanding as you're going to get with it. I'm not saying that. I'm just saying you can gain a very deep understanding of some things and a very broad understanding of everything, but you're not going to gain a very deep understanding of everything that happens as far as the internet is concerned. But anyway, that was just an introductory thing anyway. It didn't really, illuminate a whole lot other than the fact that a network is a bunch of computers connected to each other, talking to one another, usually, with some sort of input and output. And it's the means through which, computers communicate and stuff like that. They sort of touched on the fact that there is a thing that exists so that computers can communicate with one another. But again, they didn't really get into the specifics of anything or anything like that. But that's what we're going to spend at least a little bit of time doing. We're going to sort of discuss a few different concepts and things like that, like as far as networks are concerned, so that you guys will get a little bit more familiarized with it. So computer networks. A computer network is two or more connected devices that can share resources and or exchange data. Simply put, that's what it is. There's no requirement for those computers to do anything with that data other than just share it. As long as they're exchanging data, they're considered a part of a network. Sharing resources as well is something that happens. I mean, if you've ever seen like Folding at Home or SETI at Home or any of those things, that is a resource sharing, like an example of resource sharing, because what they're essentially doing is they're recruiting other computers through the internet to add to their processing power. Like folding at home is they're taking proteins and they're folding them to see, how they develop and things like that and how they interact with the body. But that is a highly computationally expensive process, incredibly computationally expensive. And, they can buy supercomputer time, or they can have people download a free program that basically receives bits and pieces of protein folding, simulations and let the computers calculate that stuff. That way, they've got thousands of people around the world that are doing that work for them. Same with SETI at home. SETI, S-E-T-I, Search for Extraterrestrial Intelligence, is a program which basically just involves a couple of different complexes of or fields of radio telescopes that just listen to radio waves in the universe. They just point at small sections of the sky and they listen. And the whole point is that some sort of intelligent technological civilization like ours, like we, every day, every minute of every day since the invention of commercial radio, have been sending radio waves out into space, and they have been structured radio waves. And there is theoretically no end to those structured radio waves. They travel at the speed of light, so there is a limitation there. So something, 5 light years away is 5 years out of date if they're able to pick up our signal. But theoretically speaking, somebody 14 billion light years away at the other end of the universe, assuming we're on one end, at the other end of the universe, can 14 billion years from now pick up our signal. Now, that's not strictly speaking true, just because if you imagine, so basically the signal gets weaker the further away from Earth it goes, for the reason that it gets distributed over a wider area of space. Imagine drawing a picture on a balloon and then blowing that balloon up. And the larger the balloon gets blown up, the more distorted and stretched out that picture becomes. That picture is a structured radio wave, which means that if you're trying to look at this picture through like a I don't know, like a small like eyeglass or spyglass or something like that, eventually the balloon will theoretically get large enough that you're only getting a part of the picture, and it's not going to make any sense to you, and it's just going to look like random noise. So that's one of the problems that can exist with SETI is the fact that if there is life out there and it is communicating with radio waves, the chances of us detecting it are very, very slim, just because those radio waves will probably be incredibly distorted by the time they get to us. But that's neither here nor there. The fact is that it's an attempt to find somebody else out there in the universe. It's an attempt to listen, and there's a lot of data to process, so you can offload it to other computers in order to process through that data and find patterns, find perhaps signs of intelligence, at least find structured, regimented, sequences in radio waves, radio signals, that could hint at the possibility of something. So there you go. So now, a node on a network is a device that connects to the network, and it is a single point on that network. So if you imagine a network as a bunch of things connected together, a node is one of these circles. These would be where your computers and your smartphones and your smart toasters and stuff are. Those would be nodes on your network. So node to node is two computers connected together. It is literally just a simple network, boop, boop, or a simple part of a network where it's just two computers connected together, node to node. One node to the other node. Pretty straightforward. Now the link is the medium that connects the nodes. So again, back to this example, this would be a link. That's pretty straightforward. Also, a link wears green. Sorry, couldn't resist. A hop is an intermediary pass the message, pass of the message along to its destination. So let's say that we had a starting point here and an ending point here. This area right here would be a hop, or this one could be a hop depending upon the path, because it could travel along this set of nodes right here, and this one wouldn't do anything with the data. It would just pass it from one link to another link, and that's its only purpose, and that would be considered a hop. Or it could pass along this area right here, and again, this computer, same deal. It's just passing information from this link to this link, so it would be a hop. Now, routing is selecting paths in a network along which to send a message. Pretty straightforward, like think of routing on train tracks. So you've got two sets of tracks, and one set goes off and one set continues on the same path. And you can think like in the old, a lot of times this is automated now, but the old stereotypical things, there's a lever, and you can flip the lever and it will switch the direction the tracks are pointing. That is a form of routing. That is exactly what's going on here in our example with the two different ways that the path, or that the data could move. The decision to move it down one path or another is routing. Pretty straightforward. Now, IP address. An IP address is a unique numerical label that allows other devices to locate a device on the network. Whoops. So you can kind of think of it like a phone number or an address. Hence IP address. Internet Protocol address is a unique numerical label. And if you've looked at an IP address, like I'm not going to, you can go into Google and type, nice Liam, you can go into Google and type what is my IP, and it will return your usually IPv6 address, although it largely depends upon your internet provider. Some are going to provide an IPv4 address, which is just an older version. Yeah, well, in my experience, it's been more often than not IPv6, but it could just be because I keep hopping to internet providers that use IPv6. Well, IPv4 is more widely utilized. If you're trying to play a game with somebody and it asks for an IP address in order to play online with them, it's looking for an IPv4 address, not an IPv6. IPv6 looks very different. So there's that. But either way, they're both going to be IP addresses. It's just they're different representations of the same thing. I believe IPv6 exists in order to accommodate a larger range of addresses so you can have more computers connected to the internet. So in order to get our easy to remember names to an IP address, so we have our computer names, like whatever you named your computer when you first set it up or whatever. We use a service called a DNS, or a domain name service. When we're given a network name, the name of our network at home, an application will ask its DNS server for the corresponding IP address so that the application can begin the routing process of getting a message to its destination. So we can give it our own network name, and we'll get 127.0.0.0 because that's, or 0.0.1 oftentimes. That will be your router, generally, when you're referring to your own home network. Anything that starts in 127, that's referring to your own home network, other computers on your network in your house and stuff like that. But anyway, we might be saying like, oh, okay, let's go to google.com and we'll send google.com to a DNS, and the DNS will return the IP address so that our computer can then go, okay, so, or router can go, okay, it's this IP address, so we'll need to send our data through these nodes, basically create this path through these nodes in order to reach our destination, which is the IP address that the DNS returned to us. So, in essence, we give them a network name, Google, whatever. We get back an IP address. The router uses the IP address to trace the most efficient path that it possibly can. Not necessarily, but generally it tries to find the most efficient path that it possibly can to that IP address. It's like saying, it's like going to a guy and going like, hey, yeah, similarly, we look up someone's name in the phone book to get their address. So it's like saying, okay, I need to find out where Jim lives, and then you look up Jim's name in the white pages, and you get his address, because that's a thing that still exists. You get his address, and then you can pull up his address on a map and plot a course to his house. You're going to say, oh, I'm going to make a left onto Main Street, then I'm going to make a right onto Elm Street, and then I'm going to make a left onto, Hyde Street, whatever. Those are the three parts of the process: the DNS request, the IP address receipt, and then the routing. So yeah, like our mailing address, IP addresses are unique. They uniquely identify a node on the network. Unlike mailing addresses, every time a computer connects to a network, the IP address can change. Imagine like your house is moving around. Because the IP address can change every time a computer connects to a network, there needs to be some address that doesn't change. And this address is called a MAC address. A MAC, or Immediate Access Control, address is used to uniquely identify the physical device that allows a node to connect to a network, e.g. a network card or a router. So there's a MAC and there's an IP. We do routing with the IP, but you can also, when you need to, return a MAC in order to be able to identify the exact location of a unit on the network. So if we wanted to Prompot. If we wanted to do a little why is it ifconfig? It should be. Anyway, if we want to do a little experimentation, we could actually start up the command prompt, or the terminal window if you're using Mac or Linux. And here we've got our system32. I can type ipconfig / good thing I did that. Wow, good for me. Network safety. Don't ever put your don't ever pull up your network address and put it online. Never. Don't do that. Don't do what I just did. You can do it on your computers, but yeah, I know you do. You just told me what your IP is, 127.0.0.0. But don't do what I did. Anyway, in this example here, this is somebody's... Oh, it's really localhost? Oh, okay. I'll never find you now. This is actually somebody's IP address here. Well, okay. It's good for the example though. As you can see, they've highlighted the MAC address in red. They've highlighted the IP address in yellow, and look, IPv4. And it doesn't look like they provide an IPv6 here. In my experience, 138 is not internal. This is true. It can be. Yes. But I wouldn't count on it being an internal IP. especially because the DNS provided is 138. Oh, there's the IPv6. It's hidden behind that. Oh. I don't know where you pulled this information from, but anyway, yes. So, fun fact, this physical address, you notice how it's got letters in it? This is just an aside more than anything else. It is hexadecimal because you need an easy way to represent binary counting. You can use hexadecimal. A single digit of hexadecimal can represent 4 binary digits. What do I mean by that? Well, whoops, don't save. What are all the different combinations of that? Let's see. 1, 2, 4, 8. Yeah. Well, oops. I can count in binary. And then repeat all this again, except with this, instead of the 0, it is a 1. Oh, and I forgot. Doy. Anyway, this is 0 to 15 in binary. You just move sideways, incrementing from 0 to 1. You know, just like when you're counting 1, 2, 3, and so on, and you hit 9, you hit 1 over here, and this goes back to 0. The same thing's happening in binary, except it's a base 2 system. So there are only 2 options, either 0 or 1. So as soon as you hit 1, it's like hitting 9 in your base 10 system, and it becomes, you move over 1 digit, and you start incrementing that one. So this is equivalent to 0, and 1, and 2, and 3, and 4, and so on and so forth. The reason why it's 4 is because this divides neatly into bytes. You can have, a byte is 2 of these. So you can represent an entire byte with 2 sets of 4, because that's what a byte is. Now, this goes up to 16. If we wanted to count in base 10, that's all well and good. We would know it's 16, but the problem is there's no easy way to represent that with a single character, and the math starts to become weird. That's why programmers invented hexadecimal. Same deal. This is 0, this is 1, this is 2, 3, 4, 5, 6, 7, 8. And this is just extraneous information. You don't really need this. 9, but instead of hitting 10, it becomes A, B, C, D, E, F. Why do I have extras? Oh, because I have a double here. Yeah, I have additional ones. So 0, 1, 1, 1 should be 7, and 4 ones should be F. I accidentally did 0, 1, 1, 0 twice because I don't know how to count. Anyway, it goes from 0 to F, and then it becomes 10. So 0, F, and then 11, and then 1F, and then 20, and so on and so forth. It's a base 16 system because then you can represent a byte with 2 hexadecimal numbers. So this is 6 bytes of information. Anyway, Not really anything you need to know, that's just an aside. I always think is kind of interesting. So a server is a computer or a program that provides specific services on a network. For example, an email server directs emails. What do you think a web server does? Well, a web server directs traffic, web traffic. Um, that's the standard mail transfer protocol. Um, so an email server is also an SMTP server. Um, but yeah, that's an example. Now that's a server. A host is any computer connected to a network. Servers are just programs that run on a host. So, um, and now it says here is a computer or a program. When they mean computer, it's just a specialized one because it only has one program running on it. But you can have a host run a server program on it and then, be doing other stuff as well. Yeah. Then you got the local area network, or LAN, which is a group of computers within a distinct area, such as a school or an office building or a house or whatever. This is a geographic distinction. Um, if you've got two computers directly connected to each other across the planet, it wouldn't be a LAN, um, because they're not part of like the same network. If they're a part of the same network, though, and in roughly the same geographic location, totally a LAN. Um, became very familiar with the term LAN because that was back in the days when multiplayer, you still had LAN parties and everybody would bring over their computer and, you know, set up and just have a wonderful time playing video games. How data packets move. And this is just sort of a fractal image representing different pieces of information on the internet, which is pretty cool, but yeah. Okay, so here's another timeline depicting major internet events. So, birth at UCLA is the I guess the internet. Well, part of the ARPANET. It's a separate thing though. Uh, email was introduced in 1972. The ability to share discrete collections of words, letters, through an internet style thing, or a network. Then TCP, the transfer protocol that was on that video. Then IP, the Internet Protocol, IPv3. Wasn't until about 1983, though, that the TCP/IP was adopted as the Internet standard, even though this stuff was developed 7 to 10 years earlier. And DNS happens a year later. Then you've got all your domain names like edu and gov, and aside from just the .com. Then the World Wide Web with internet service providers, late 80s. Oh, .com was open to public. Okay. Yeah, 1991 is really where the internet starts to explode, because internet browsers start to appear. They start to be bundled with operating systems and freely available, and ISPs start selling internet to people, and it becomes a big thing. IPv6 comes out in 2000, but we're still dealing with IPv4 as well. I say dealing with like it's an issue. I actually like reading IPv4 more. Um, it's much easier to deal with, and a lot of people are more willing to deal with IPv4. 2009 is very clearly not now. So there's, it's a bit outdated. But this is the history of the internet up to 2009. As you can see, there's a whole bunch of branches and stuff like that, which was covered in the video. How it was all sort of developed concurrently and melded into the internet. This is part of what I mean when I say that the internet was sort of developed organically. TCP/IP was adopted as the internet standard, thankfully, so that computers could communicate, but there's still a lot of strangeness out there. As you can see, 1 million people were connected around 1991, 1992. By 2005, 800 million, a billion, or no, by 2004, 800 million, a billion by 2006, and I don't know, 3 billion? This is just based on websites. And then as you can see, our internet speeds have also gotten faster. 56K was a big deal though when I was younger, as far as public access internet was concerned. I mean, T1 was a big deal, but like people couldn't really get T1 or T3. Here's a lovely picture of Tim Berners-Lee. He's actually been very instrumental in the internet that you're familiar with today. It's said that he's the inventor of the World Wide Web, basically the communications protocols and things like that that enable users like us to navigate through the internet and go to different portals or other web pages and view data in a very user-friendly and easily digestible fashion and navigate them easily and things like that. Yeah, web pages that we see in our web browsers make up the web, the network of interconnected computers around the world that enable us to see those web pages make up the internet. There you go. The internet makes info available via a global computer network. The web makes that info easy to read. And then we've got to talk cyberspace is an internet metaphor. That's going to be a video for another time just because we don't really have enough time to go through it. But it is an interesting thing that sort of illuminates the different areas of the internet with metaphors so that it makes a little bit more sense. But yeah, so this was an interesting sort of introduction to cybersecurity, learning about networks and things like that. Hopefully it made some sense. It'll make more sense as we go through more of this presentation and we learn more about how these things interact. If you find it interesting, I encourage you to spend some time reading up on the stuff on your own as well. But otherwise, that's going to go ahead and do it for today. I'll do the poll questions and we'll do question and answer time, and then we'll break for the weekend.